Cities on the Moon? Cities on Mars? Or maybe it's better to build space cities on an asteroid, or from an asteroid. The idea seems crazy and far from obvious. But interestingly, such space settlements could in some respects actually be better than bases on Mars. The other question is, why do we even need this? I asked the same question discussing the colonization of Mars. Considering how complex and expensive this task is, it's still not entirely clear what it's all for. Spending tens, maybe even hundreds of billions of dollars to relocate people to a planet where conditions are far worse than in Earth's deserts or Antarctica, and where, last time I checked, there was still plenty of space. Building space settlements might seem impractical right now, but that doesn't mean it will always be that way. And that's not even mentioning the spirit of exploration and scientific curiosity. Right now, several space industries are already being discussed or even in their early stages, like space tourism, space resource mining, we've talked about that too, manufacturing in microgravity conditions, building space power stations and transmitting energy back to Earth. Robots won't be able to handle everything everywhere, and humans will still be needed. And humans need somewhere to live. And that's why space bases and cities on or made from asteroids are a pretty interesting solution. And this concept isn't just found in science fiction. There are already some scientific papers on this topic discussing various approaches to it. How to build the space city of the future? Why our asteroids might be better than Mars and the Moon? Is this even possible? We'll talk about all this and more. I'm Andrei, and this is Cosmos Elementary. When we think about creating space bases with a permanent human presence, the first places that come to mind are the Moon, Mars, and space stations. Each of these options has its own advantages and disadvantages. If we choose from the planets, Mars seems like the most obvious option. It's not as close to the Sun as Mercury, and it has at least some atmosphere. The conditions aren't as extreme as on Venus. Gravity is weaker than Earth's, but still enough to allow for a relatively familiar way of living. But the atmosphere is still very thin and unbreathable, temperatures are low, there's no global magnetic field, and no proper protection from cosmic radiation. And the journey is long and far as well. The Moon is closer, but it has the same problems with the atmosphere and radiation protection. Plus, there are huge temperature swings between lunar day and lunar night. Whether it's the Moon or Mars, it might be a good idea to go deeper beneath the surface and set up a base inside, say, a lava tube. Space stations, well, the advantage here is that we've already been doing this for several decades. But it's one thing how it looks now. In low Earth orbit, inside Earth's magnetosphere, on a relatively small scale. But if we want to build something much larger, where hundreds or even thousands of people will live permanently and farther away, then we'll again need to take care of radiation. For a large station, transporting materials or components from Earth would be very expensive, and on top of that, having many people live continuously in conditions of essentially zero gravity. Here we could build O'Neill cylinders, a concept described by Gerard O'Neill back in 1974. A station consisting of a pair of cylinders, each 8 kilometers or about 5 miles in diameter and 32 kilometers or about 20 miles long, rotating in opposite directions. And thanks to the rotation, artificial gravity is created on the inner surface of these cylinders. In principle, this is possible, but again, building such a large-scale space structure and transporting all the necessary materials for it would be very challenging. In general, each option has its own advantages and disadvantages, and challenges. But the idea of using asteroids has some interesting benefits. If we compare it to Mars, for example, the red planet, though less massive than Earth, is still heavy enough to pose additional challenges. With a base on Mars, where ships land and take off from the surface, you'll need a significant amount of fuel, less than for Earth, but still quite a lot, to overcome the planet's gravity. And when landing on the planet, you also have to account for its gravity to, well, avoid crashing. Near-Earth asteroids can be closer to Earth than Mars, Plus, since they follow elliptical orbits of varying eccentricity, these asteroids can also serve as a kind of transport vehicle, because at different points in their orbit they come closer to other bodies in the solar system. Also, it is possible to create protection against cosmic radiation on asteroids, as well as create artificial gravity. We'll talk about all this in more detail with specific examples coming up. A city on an asteroid might sound great in theory, but what would it actually look like in practice? It would be great to have some concrete concepts that explore the various aspects, and such concepts do exist. The first one we'll talk about is described in quite some detail in this article authored by David Jensen. Here we're not just landing on an asteroid and building a small base on it. We're essentially reconstructing a significant portion of the asteroid's mass into a station, and the final structure and scale is comparable to the entire asteroid itself. The article is actually very detailed, covering many aspects thoroughly. We won't go too deep into here, but we'll go over the key points. The article can be divided into three main parts. The first question is which asteroid to choose and how to select it for making a station out of it. The second is what the structure of the station will be, and the third is how to actually build it. Let's start with the selection of the asteroid. What's interesting is that the article doesn't just discuss the necessary parameters. It actually considers known asteroids and, based on those parameters, selects a specific real asteroid that would be best suited for implementing this kind of plan. In fact, there could be a large number of asteroids that are suitable for reconstruction. Very small bodies aren't of much interest to us, but the larger the object, the rarer it is. Still, the number of potential candidates could reach into tens or even hundreds of thousands. And yet, one of the key factors considered in this selection was the properties of the asteroid's orbit, as this directly affects the cost of the mission. Let's say we chose an asteroid whose orbit has a high inclination. That would require additional changes in the velocity of the spacecraft flying there to build the base, which means more fuel, more mass, and a more expensive mission. So the author of the paper set certain limits on the inclination of the orbit and the size of the asteroid. The selection was also made in favor of asteroids located within the habitable zone of our solar system, so that it would be easier to regulate the temperature on the constructed station later on. This narrowed the range down to 5,570 candidates. Further restrictions were then applied on size, from 500 meters or 1,600 feet to 5 kilometers or about 3 miles, which is understandable, and also on rotation speed. As we remember, we also want to create artificial gravity. Most likely, the asteroid's initial rotation speed around its axis won't be enough to create gravity close to Earth, or even a significant fraction of it. So the asteroid's rotation will still need to be accelerated, but the higher the initial speed, the better. Taking all this into account, along with the known parameters of the asteroids, the list of candidates was reduced to 87. And then from this list, taking into account the ratio of the cost to reach the asteroid and the potential value of the asteroid, its type and composition, the majority were eliminated. Only 6 remained, and the final choice fell on asteroid 163693 Atira. It is a fast-rotating S-type asteroid, approximately 5 kilometers or 3 miles in diameter. It even has its own satellite, about 1 kilometer in diameter. The article considered several possible station shapes, including a dumbbell shape, a sphere, a cylinder, and a torus. The choice fell on the torus. Later, however, the shape was further modified. It was made more elliptical, so the cross-section of the station looks like this. But how to actually build it? Well, that's where it starts to get into the realm of science fiction. The asteroid would have to be reconstructed into a space station by self-replicating robots. Ideally, this could be done with just one space launch. We load several tons of high-tech equipment and initial robots. The capsule is delivered to the asteroid. There, the robots begin manufacturing thousands of other robots, using the material of the asteroid itself. And this whole crew then uses the asteroid's material to build the station. They melt the soil, produce special glass, and create metal structural elements, wires, solar panels, and so on. At the center, the part of the asteroid remains as the core structure. Up to 30% of the asteroid's material is processed into the station. Columns extend outward from the center, supporting a ring with a main radius of just over 2 kilometers or 1.2 miles. And the elliptical cross-section measures about 1 kilometer along the major axis and 334 meters or 1,000 feet along the minor axis. Inside, it is proposed not just to live on the surface where artificial gravity is created, but to make the structure multi-level. Here there are 17 floors. On top there is a large open space and also 82-story towers. Just on the top floor alone, it could be possible to accommodate 400,000 people. And taking into account the other floors, the maximum capacity is 21.5 million people. But of course, for a more comfortable life, it would be better to limit it to about 3 million. There is an interesting aspect about the multi-story structure. The strength of artificial gravity depends on two parameters: the station's radius and its rotational speed. This means that on different floors, the distance from the axis of rotation will vary and consequently the gravity will be different. For this station, the goal is to achieve gravity close to Earth's, and the upper floors and the towers will have the weakest gravity, while the lower floors will have the strongest. It's better to use the floors around level 1 for residential areas, and the lower ones could be used, for example, for strength training. The article even includes very rough estimates of how much this whole project might cost. The result is a very optimistic figure of just over $4 billion. As you remember, only one launch is planned, and after that, everything builds itself there. People still wouldn't arrive to a fully finished setup, because the final, more delicate work would still need to be done, creating conditions for a breathable atmosphere and a temperature suitable for humans. But still, considering that the station could eventually have up to 1 billion square meters, that comes out to just $4 per square meter, or about 40 cents per square foot of previously non-existent usable land in space. If we believe the information I found on the internet, the artificial island Palm Jumeirah in Dubai cost $12 billion. That means the price per square meter of land there is over $2,000, and here only $4 in space. Just one tiny little problem. We currently don't have the technologies ready to make this all happen, and it's not like they're actively being developed for this purpose either. The article itself is more of a concept development rather than a practical step-by-step guide. It's a discussion about what could theoretically be done, but it doesn't seem to contain anything fundamentally impossible. But there are other approaches as well which are quite different. If the previous concept suggested using the material from the asteroid's surface to build the station around it from the outside, this article discusses exactly the opposite. To excavate rock from inside the asteroid, create a cavity there, and arrange the base inside it. The need to create such settlements on asteroids in this article is again motivated by the fact that in the future, mining of useful resources might be carried out on them. Asteroids may already have natural cavities inside them, where theoretically a base could be set up, and this could even provide a certain level of protection from cosmic radiation. But the main reason why the authors are not satisfied with this option, and why they suggest going through the trouble of digging a huge cavity themselves, is gravity. We've already touched on the importance of gravity today, but it's all certainly not just about comfort, though that's also important for long-term habitation. But from studies conducted on the ISS, we know that prolonged stays in microgravity affect human health. While some plants on the ISS adapt fairly quickly to weightlessness, us humans not as much. In short, if we want to live properly on asteroids, creating artificial gravity is an important thing. As you remember, in the concept we discussed in the previous part, the idea was to create gravity close to Earth, that is, at 1g. That would of course be ideal, but the question is how realistic it really is. I already said that the strength of the artificial gravity depends on the angular velocity of rotation and the radius of the rotating ring or cylinder. If you've ever been on such rides, you know that the faster they spin, the more strongly you're pressed into the seat or the wall. And here you need to find a balance between the structure being able to withstand a certain rotational velocity without being torn apart. And for example, on very small stations, people might start experiencing effects of varying gravity. A few years ago, PBS Spacetime released a video where they analyzed some sci-fi examples of structures that used rotation to create artificial gravity. And for example, the ring on the spaceship from 2001 Space Odyssey could create artificial gravity, but given its relatively small size, the gravity felt at the person's feet and at their head would be noticeably different. In the previous example, the scale was on the orders of kilometers, but if the station or ship is much smaller, then the gravity acting on a person's feet and head would differ noticeably. This leads to various quite tangible effects like the Coriolis force, which affects the vestibular system. In fact, it wouldn't just be hard to run, even walking on such a small station would be problematic. On the other hand, the rings from the Halo game series are more realistic in this respect. People could walk around there comfortably. But then the question arises about the strength of the material these structures would need to be made from so they wouldn't fly apart. And in general, how do you build such gigantic structures where the diameter measures thousands of kilometers or miles? And in this article, they suggest simplifying the situation by not striving to create Earth-like gravity of 1g. A person can quite well live under gravity levels of Mars. That is about 38% of Earth's gravity. And achieving such gravity is basically possible by spinning an asteroid a few hundreds of meters in diameter. By the way, the article does not really focus on how exactly the asteroid is planned to be spun up. We'll talk about some of the ideas in the next part, but here the idea is also mentioned that the additional momentum to the asteroid could come from spacecraft taking off and landing on it during the station's construction and development. Here is a rough sketch of how it is supposed to look. A hollow cylinder inside the asteroid and artificial gravity on the spinning asteroid is created along these walls. The main focus of the article is on whether the asteroid will hold together or break apart when spun up to the speed necessary to maintain gravity at 38% of Earth. Naturally, this depends on the structure and composition of the asteroid, and the article notes that we don't know much about asteroids of this size, so certain assumptions were made. They considered a model of a solid, monolithic and homogeneous asteroid, and the calculations in the article showed that in principle, under certain conditions, the asteroid should withstand the required rotational speed, making it possible to create such a base inside the asteroid. It's just, there's one little problem. In the previous scenario, we considered a hypothetical asteroid that is essentially a solid piece of rock, which, at certain sizes and rotational speeds, should withstand spinning up without flying apart. In the solar system, there are bodies that rotate at speeds close to the critical limit, and this is noticeable from their shape. For example, the dwarf planet Haumea, which given its mass and composition should be spherical, but due to its very high rotation speed, it appears to be significantly flattened. Or asteroid 1999 KW4, which also rotates very fast, resulting in a shape like this one, with a ridge forming along its equator. If these bodies were to spin even faster, perhaps not by much, they would likely break apart into pieces. And the previous article considers quite borderline cases. Some bodies can withstand the required rotation speed, but there is a little margin for maneuvering. And here is a newer article. Its authors refer to the previous paper and say that it contained one serious error. Most likely, most people, when they think of an asteroid, imagine a huge chunk of rock in space. Such asteroids do exist, but not all of them are like that. It also depends on their size. The new article states that asteroids which are solid coherent pieces of rock are usually quite large, from 10 kilometers or 6.2 miles in diameter and up. The mass of such asteroids is sufficient for the object's own gravity to create enough pressure to compress the pile of separate fragments from which the asteroids formed into a single solid body. And, as we remember, the previous work dealt with an object several hundred meters in diameter. And today we know that objects of that size are most likely what are known as rubble piles. In other words, it's not a single solid piece of rock. It's more like a pile of loosely bound fragments that are held together only by gravity. The sizes of these fragments range from tiny grains to large boulders. We've learned a lot about such asteroids thanks to missions like OSIRIS-REx, which studied the asteroid Bennu, a small near-Earth asteroid about 500 meters in diameter that likely has a rubble pile structure. It even has a distinctive appearance. You could compare it, say, with the asteroid Eros, whose longest axis is over 30 kilometers or 18.5 miles. Now, Eros is a much more solid object. Density measurements also support this. Eros has a density more than twice as high. So what does all this tell us? Well, it tells us that the conclusions of the previous article, that an asteroid several hundred meters in diameter can withstand rapid spinning, are incorrect. Because a real asteroid of that size would be a pile of loosely connected rocks. And that pile would scatter in all directions. The asteroid I mentioned earlier, 1999 KW4, which is about 1.5 kilometers in diameter, is almost ready to do just that, as can be seen from its shape. But the most interesting part is that this does not rule out the idea of building a base on a small asteroid. By the way, smaller asteroids interest us precisely because there are simply more of them, so there's larger selection, and the scale of work is smaller. So the authors of this new article came up with the way to turn the situation to their advantage. Instead of digging a cavity inside the asteroid, they proposed the following. First of all, the asteroid itself needs to be spun up initially in order to eventually achieve at least artificial gravity comparable to that of Mars. By the way, the study already provides more concrete details about how an asteroid could actually be spun up. The proposal is to place cannons on the asteroid, powered by solar panels, with a conveyor feeding them material from the asteroid itself. These cannons would fire the material tangentially to the asteroid's surface, thereby spinning it up. But as we've already established, this would simply cause the individual fragments that make up a small asteroid to scatter in different directions. And here a clever idea is proposed. An external containment system should be placed around the entire asteroid to prevent fragments from flying away. Moreover, it shouldn't be a rigid frame, but rather a mesh that expands in volume as the asteroid begins to break apart. This mesh is proposed to be made from carbon nanofibers. Here we see a simulation frame from the article. First, there is an asteroid covered by a shell. The asteroid spins up. The shell expands until it reaches a maximum size. And then the asteroid's material covers the shell with a layer of certain thickness. And in the end, if we start with an asteroid of 600 meters in diameter, about the size of Bennu, it can be transformed into a cylinder 6 kilometers or 3.7 miles in diameter, with the interior covered by a 2-meter thick layer of regolith. Solar panels can be placed on the outer surface of the cylinder, while the human settlement would be located on the inner surface. The regolith layer would provide a large area, create artificial gravity, and also serve as protection against cosmic radiation, shielding residents from solar storms and galactic cosmic rays. But since it isn't a sphere but a cylinder with open sections, at least some galactic rays will get inside. This aspect isn't discussed in the article. But in any case, the radiation levels would be much lower than if we simply placed a base on the surface of the asteroid. In the end, it basically results in something like an O'Neill cylinder, but without the need to haul a ton of material from Earth to build the station. This means that the approach could potentially be much more cost-effective. The authors themselves acknowledge that their concept relies on technologies that don't yet exist, but their work at least demonstrates the fundamental possibility and basic physics of how to transform a small asteroid into a space city for humans. So, who knows? Maybe say 100 years from now, people will live not only on the Moon and Mars, but also in numerous space cities made from asteroids. Thanks for watching. Links to all of the sources are as always down below in the description, and if you enjoyed the video, leave a like, comment, subscribe, and share this video with your friends. As you can see, I don't get many views, so you might help. Thank you. Bye.